Welcome to UBCCS 532W. My name is Frank. This is Graduate Introduction to Probabilistic Programming. And today, because I threw you into the deep end with variational inference last time in order to get it in your head the first time round preparing for the homework, today we'll do variational inference a little more slowly and sort of introduce it writ large, and then maybe the black box variational inference stuff we talked about last time will make more sense. So where are we? We've got evaluation and graph-based inference. You all know importance sampling. We talked about lightweight Metropolis Hastings, Hamiltonian Monte Carlo, Metropolis within Gibbs. Awesome. You can take programs that denote inference problems and automatically solve them in a black box kind of a way. That's pretty cool. The next homework is about black box variational inference. And ultimately, we're driving towards trying to simultaneously get you to think about inference as a problem type, problems, like way of abstractly expressing problems. This part is the hardest part, and hopefully many of you will actually engage in this in your final projects. But obviously, we've been automating inference, and ultimately, we will be going towards variational inference at the end of the term, and almost everything will be some form of variational inference for the last bit after we do higher order languages and inference in sequential Monte Carlo in higher order languages. So it's worth spending a little bit of time just talking about variational inference. So this will be the second to last inference algorithm inference algorithm family that we look at. The last one will be sequential Monte Carlo, and that will be 2 lectures from now. So I guess next Tuesday. Fine. So in particular, we're going to, variational inference will show up really a lot when we talk about amortized inference and doing model learning, parameter estimation, maximum likelihood parameter estimation in models with latent variables. So today we're going to do variational inference. And in some sense, I think actually the right way to construct a course in machine learning, or certainly a graduate course in machine learning, would be to just take NeurIPS tutorial videos on those particular subjects and just watch the videos, right? I mean, let's be honest. These are the people who really thought about these things the most in terms of how to present them and these sorts of things. So. All 3 of these lovely gentlemen are friends, and they gave an excellent tutorial at NeurIPS in 2016 on variational inference. And there's a video that you can watch here, and they're excellent speakers, so on and so forth. And these slides are basically stolen from that video, more or less directly. And if you watch it, Dave basically did the history of variational inference, which we're actually not that interested in this course. And then Rajesh and Shakir went to sort of modern variational methods and talked about those, and those we are. They formulate probabilistic machine learning using they chose, which is kind of funny because Dave is a statistician, the other 2 are machine learning people. We typically use statistics notation, and so just bear with me. So we use X and Y, and throughout their slides and throughout this deck, we're going to use Z and X instead. So Z's are going to be the latent variables, and X's are going to be the observeds. Okay, so let's just roll with that. So like we've been doing all along, we have a probabilistic model. And they don't take a Prog perspective, but we're going to take a Prog perspective, so we know that this probabilistic model is denotable in some sort of programming language, right? But whatever, it's the joint distribution of some hidden variables Z and some observed variables X. And we want to do inference about the unknowns by characterizing the posterior distribution. which is the conditional distribution of the hidden variables or latent variables given the observation. So this is a review from the very, very beginning, right? Just to recontextualize. But remember, we're going to be using z and x versus x and y. That's fine. And we know that the integral, this integral is intractable for most models, right? So we have to do some sort of approximate posterior inference. Fine. And we've talked in this course about a lot of ways of characterizing this posterior distribution, right? So we've approximated it via sampling, asymptotically approximated it through the strong law of large numbers and sampling procedures. And we touched on black box variational inference, where we said we can change this problem into an optimization problem. And this, I think, will, this, just going over their lecture slides, will make this this statement more apparent, and again, will make what's going on in black box variational inference a little bit more direct. One more change in notation. In the book and in our notation before, we used lambda for the variational distribution parameters. They use nu here. So just roll with that as well. Not a big deal. Okay. So this is an important thing to this diagram is super important, actually. So we have some target. This is the target. This is the posterior that we're interested in approximating in some sort of a way. And this ellipse is some variational family. Okay. And what we're looking at is just really the space of distributions, right? In a cartoon, right? And a variational family is going to be some subspace of the space of all possible distributions. So the posterior is going to live somewhere in distribution space. And the set of distributions Q indexed by nu and corresponding to some structural assumption is characterized by this ellipse, right? And the point of variational inference and the magic of variational inference is to try to find the member of this variational family that is within the variational family, but closest to the target posterior in some sense, some measurable sense. And generally speaking, this is not the only metric that you can use, or distance that you can use. We use the KL divergence, which we talked about last time, between the variational approximation and the posterior. So this is the notion of closeness.
I have a question.
Yep.
You mentioned it was a subspace. So does that mean we have like a vector space of like joint distributions? The vectors are joint distributions, or is it something else?
So you should be thinking while we're talking about this that there's many different levels that you can think about this at, right? So one is there's the posterior like this posterior distribution is just in the space of distributions over the space of Z, whatever the space of Z is. So if Z is a vector space, then the space that this lives in is in the set of all possible distributions over that vector space.
And are the distributions, can they be thought of as vectors in a vector space?
The only way that you can think of distributions as vectors is if you are in a parametric. So you have like there's going to be some set of parametric models in here. So there'll be like p theta. There'll be some set of parametric models, but you can have non-parametric models that don't have a vector space representation. You can have structured models that are subsets of the set of all possible distributions. Those are, like, for instance, graphical models. You can have probabilistic programs in either the FOPL or HOPL form. So all of these are different subsets of the sets of models. Okay, and the posterior distribution, whatever it happens to be, is constrained in the Bayesian sense, in Bayesian models, to be in the space of models There might be some very technical caveats to this, but the posterior distribution will live in the space of the family of models described or indexed by the prior.
Okay.
Okay.
So what's the relationship between P of Z given X and Q and this variational family?
So we're saying we're going to try to find the member of this set that is closest in the KL divergence sense.
To this P of Z given X?
That's correct. All right, so the P of Z given X is the thing that we've been trying to characterize the entire time. That's what the principal activity of the course is, automating the characterization of P of Z given X, right?
So is it not really like Q of Z V is not really like a subspace? It's more, we could think of it as a subset of like some larger set?
Yeah.
Okay.
Yeah. And V star is a particular member of that set, and that V star corresponds to a particular instantiation of this variational family, a set of parameters for this variational family. Cool. So what are we going to do? We're going to basically use, we're going to frame this as an optimization problem. We're going to use stochastic optimization, which means that we can work on very large data, and we can work with a very wide class of difficult models being over here. And we can do VI. Basically, we can specify this space in a very flexible way. In other words, Q can actually be very, very flexible. These are largely comments on the way VI was historically reposed, which was much more restrictive in its formulation. Sufficiently restrictive that there was a whole half of probabilistic machine learning that did sampling-based methods, and a whole half of and like maybe more like 80-20 for MC methods, variational methods 20. And then it flip-flopped, and then more recently, we've kind of realized that they're much of a muchness. They're kind of the same thing, and there's a lot of benefit that comes from looking at it that way. Okay, so there's a very critical thing, and this came very quickly, and you just need to see it 2 or 3 times before it gets into your head, right? There's this evidence lower bound thing, and this is the magical quantity that allows us to frame approximate inference as optimization. Okay, because again, it automatically avoids computing a normalization constant. So it's a very simple derivation, but profound in its implications for how one does approximate inference. So ELBO is an evidence lower bound. The evidence lower bound. Great. Fine. So what's going on? We did this really quickly last time, but let's do it much more slowly now. Okay. So this is the evidence. Okay. This is the log evidence. I'll use the highlighter, I guess. So log evidence is, you can think of this as the log likelihood of the data. Your data are x's. This is the thing that you have here, right? You have x's, right? So I think it's totally uncontroversial that you can express the evidence as the marginalization of the joint distribution over the latent variables, right? We also know a lot about importance sampling at this point, right? This is my favorite trick, right? So the next line of this bound construction is simply to multiply by 1. So we're just multiplying by q over x by q over x. Yeah? No problem with that. The next one, go off and get comfortable with if you're not. I mean, you can look up Jensen's equality and how it applies here. But the next line is Jensen's inequality, right? So basically, if you swap the log and the sum, you can invoke Jensen's inequality because of the some convexity arguments, right? And when you do that, you know that this quantity is greater than or equal to this quantity. Okay, so this is Jensen's. So look this up if you're uncomfortable with this. Okay, so this one you might have to look up. But if you look at what the last line is, right? The line that we're on right now, this is just an expectation with respect to this introduced distribution Q, whatever it is, right? So this is just an expectation under Q Z given nu of this ratio. Log joint divided by Q parameterized by nu. Okay, cool, fine. So this is kind of nice. In fact, it's very nice because of a couple of things. One is, and I'm gonna try to point out stuff leading into the future in just a little bit. But one of the nice things is that there's nothing here that we can't evaluate. So we can never actually evaluate a posterior probability of Z given X, but we can evaluate the joint distribution. That's straightforward. You know how to do that. You've been doing that in your programs forever. You can do that in any program you want to. You can evaluate the joint, right? And because the choice of this distribution Q is free, we would certainly choose to use a Q for which we can evaluate its density as well, right? So basically, because we have a free choice, that's great. And we also can choose a Q that we can sample from. Why would we not, right? So basically, everything in this term are things that we can deal with. We can deal with the joint distribution, we can evaluate it and get a number, we can sample from Q, and we can compute the score of Q, which is basically the log density evaluated for some parameter nu and some input Z. Okay. The other thing that's super cool is that, you know, if you look at this, right, and I think I did this very slowly, or I did this last time as well. Then you can see that this term has no Z. So it comes out. And the remaining term, if you squint at it, is the negative KL divergence between our QZ and PZ. Right? Because this is, I mean, yeah, that it's just EQ. That's this bit, right? Plus this expectation. So that's what this KL divergence is, okay? And again, I said that the things you need to know about the KL divergence is KL is 0 if P Z given X is equal to Q Z given nu. That's pretty much what you need to know. Which means that if you okay, so now this is this magicness is pretty straightforward. If you can, okay, so there's steps, thinking steps. Let's get to it, right? So we're going to operate on the ELBO. So this is the ELBO, which is a parameterized by new, equals this thing, right? That's the ELBO, right? So what happens as we attempt to maximize the lower bound? Well, to maximize the lower bound means this term stays the same. It's constant, right? But maximizing the lower bound means making this, driving that to 0 as much as possible. When we attempt to maximize the ELBO, we are implicitly driving this k-odds divergence to 0. And I can tell that at least one of us is very distracted today. So I want to make sure that once you see this, then the rest is almost automatic. But I want to make sure that you see that what we're doing is we've constructed magically an objective that we're going to try to maximize. Right? When we maximize this, we're implicitly, even though we're going to operate on this is the thing that we're going to operate on, right? But what we're implicitly doing is driving this KL to 0, because in order to maximize the ELBO, the only thing that can move is Q, and the only thing that can happen is that this KL can get closer and closer to 0, which means that the evidence lower bound will increase up to a ceiling, which is the evidence of the data under the model. Okay.
Can I ask a question about this?
Yeah, please. Yeah.
So I've seen this derivation many times, and it's always appeared like a little circular to me, or maybe not circular, but just like you can sort of see it from different angles, I guess.
There's lots and lots of ways to look at this. Yeah. But go on.
So,
yeah.
So is one of the ways to look at this to say that we want to approximate the true posterior with Q. However, because we don't have the normalization constant, we can't do that. So what we're going to do is we're going to minimize the difference to the joint. And the gap in between is the evidence, which is precisely that factor that we don't know. Is that a way of looking at it as well, or?
Yeah, I mean, yes, obviously, because we have the relationship here, right? You can look at it that way, but I'm not sure that that's a helpful way of looking at it. The other way that sometimes people look at this is they break down the loss in the following way, which is you can also write this as EQ P of X given Z. Sorry, that's got to be a log in front of that. Log of P of X plus EQ log P of Z, Q of Z. Right, which you can also look at as, again, some sort of EQ log X given Z minus KL QZ new PZ. Yeah. Which is so this view of the ELBO says that there is some regularization, which is here, which is to say we want the variational family to look like the prior, but we also want, in expectation, the data to be well explained. So there's like often people will refer to, particularly in the variational autoencoder space, people will talk about this as a reconstruction loss and this is basically a regularization. I don't find that perspective particularly helpful. I think that really the only thing that you have to think about is this perspective down here, which is that there's a gap that's being minimized. And like when we're learning new, we're specifically, even though we're operating on the ELBO, the goal, the objective is to drive the KL to 0. And it just so happens that if you operate on the ELBO, that happens, and it's so super amazing that in order to operate on in order to operate in the ELBO, you don't have to consider, normalization constants. That's the really amazing thing, right? Now, just to put this out there for future proofing for our class, eventually, just to throw this out there, we're going to be doing model learning, and I suggested that we're going to be doing that as well. And this thing is going to be parameterized as well by some parameters, right? So in other words, the joint distribution will be parameterized by something. And if you notice, what's really nice is that if we want to learn the model parameters, maximum likelihood says we would like to learn the parameters of a model that best explain the data, which is X, integrating over the latent variables. Okay? So this objective gives you a mechanism for doing model learning in latent variable models, effectively by using the importance distribution to integrate over the latent variables for you and perform simultaneous model learning and inference network learning. Okay, so being familiar with this ELBO and the derivation is super important. Okay, it's kind of instrumental to understanding what's going on with the rest of the.
Is Q the importance distribution? So when you said importance distribution,
yeah, I mean, if you think about what we do in importance sampling, we're when we importance sample from an unnormalized density, what do? We evaluate the unnormalized density on top, and we have an importance distribution that we sample from and then score from. So you can look at this as a weight, in particular an unnormalized weight.
Okay. So wait, which is the importance distribution?
Q.
Okay.
And is the universe?
Somebody said something I couldn't hear.
It may have been my background noise.
I see.
Sorry.
More questions? Okay, cool. So there is a history, and I'm going to skip over the entire Dave Bly section of the tutorial because, again, it's not actually helpful to thinking about variational inference in its modern incarnation, I think. But just to tell you, it's possible, particularly in the FOPL kind of context, to construct queues in the way we're looking at on this slide, and then look at the factorization of the joint and look at the factorization of queues and separate this integral into small subsets of variables in which some of this integration can be done analytically, okay, even under Q. In particular, you can make use of conjugacy relationships again in sort of weird ways to get you because these can, depending on the structure of Q and P, look like posterior predictives. So historically, and this is the reason why historically, maybe up until even 2000s, the early 2000s, maybe even mid 2000s, variational inference really hadn't taken off. Maybe, I mean, basically autodiff again changed variational inference. So the history of variational inference was you do one-shot inference. You write down a model, you very carefully choose your variational approximation, then you derive manually or approximate the expectations that arise, and you derive gradients with respect to variational parameters, and then you solve fixed point equations. And it's if you actually look at PRML or something like that, it smells different to what's done in practice now. You do a coordinate-wise ascent, basically, a block coordinate optimization rather than bulk optimization. The sort of modern view is to say we just use gradient descent to maximize the ELBO. Right? And what do we need for this? We need an evaluable, right? We need a sampleable proposal. And ultimately, because the way we're going to do this is we're going to write a gradient with respect to nu here, and then we're going to write a gradient with respect to nu here, we need to be able to deal with gradients of expectations. Okay? And a lot, in fact, arguably, the bulk majority of deep probabilistic programming and probabilistic programming in its modern incarnations is about just dealing with gradients of expectations. And the key idea, really, particularly when we talk about variational inferences, we're going to use stochastic gradient descent relying upon the unbiasedness of Monte Carlo integral approximation. So we're going to say that this thing is approximately equal to, the sum from k equals 1 to k, 1 over k, whatever, doesn't really matter, of log p z x z k q z k nu. Okay, so we know that this is unbiased. We derived this in lecture 4 that this is unbiased, right? Which means that we can not quite. This is I should get rid of this. E q of this is approximately equal to that, right? Forget the gradient for a second. So we use the unbiasedness of Monte Carlo approximations, integral approximations, to allow us to think about doing stochastic gradient. Okay. But what do we need to do? All right. So we're gonna look at this. So just look at this for a second, right? So we're gonna write down g of xz. I guess let's make sure that we see it. G of xz is equal to log p of xz minus log q of z given nu. Okay. So this part right here, we're just going to call g. Okay. So we're going to define g. And now we do some calculus. Right? So what is grad nu of the ELBO? Okay. Well, it's not so bad. We started doing this before. The grad nu of the ELBO here is just the gradient of the integral, or the expectation. It's EQ of the inside G, right? So we've just made it simpler to see what this is. So G is, we can even drop the dependence on X because X is everywhere, okay? It's just constant. Cool, all right. So if we assume sort of reasonable behaviors, we can exchange the integral with the gradient with the integral. That's what happens here. And then we apply the chain rule, right? So we've got the gradient of Q times GZ plus QZ times the gradient of G with respect to nu. And this is still integrated over dz. Okay. So this is the thing that I did last time that was arguably too fast, right? So if we use this, which is equivalent to Q times grad log Q equals grad new Q, right? So this is just rearranging this right here. If you look at what happens here, that's this. So we substitute in Q grad log Q here times GZ. And this side is unchanged. Now we have kind of a cool thing that's happening, right? So now we have these Q's, so we can factor them out, and this becomes an expectation now over our variational distribution of grad new log Q times G plus grad new G. Okay. And now we've got a couple of different ways that we can go. BBVI is in this family. And then later on in the course, we'll be talking about pathwise gradients and mixtures of the two. Okay. So score function gradients of the ELBO. That's what we're going to do next. All right. So we just derived this. Right. So it's nice. We have. Let me back up and just explain why we want to do this. Right. If it isn't obvious, is this obvious to everyone? I guess that's a question I could ask. Is it worth? I don't know what Emma's doing. She's typing emails or something during course. I don't know. I'm working on the homework. Mia, is this obvious what we're talking about here? The homework. Yeah. So let's motivate why we're doing this crap, right? This is a bunch of algebra. Why are we doing this? Well, G is not a distribution, right? It's something. Q is a distribution, but unfortunately we need to evaluate the gradient, right? And what we'd really desperately like to do is rearrange this into something that allows us to sample from Q. So the whole point of all of this mumbo jumbo is to get Q out here in a form where we can sample from it, right? And evaluate everything else, right? So this is stuff that we can evaluate. This is something that hopefully we can evaluate, right? And notice, just to be clear, I always get messed up with this, right? This is like so, right? This grad applies only to the Q here. This is going to be part of the BBVI thing as well, right? All right. So this has been rearranged specifically to put an expectation over Q out here and make everything else evaluable, right? So fine, we've done this rearrangement, right? And we've got an expectation over Q, and we've got this grad log Q thing here, which is annoying but doable in basically every instance. Then we have this G thing, which has been sitting around for a little while, and we have this grad new G Z V thing here, and this should be a bold Z, but whatever, doesn't matter. Fine. So this thing actually simplifies in a nice way, which is to say this expectation here evaluates to 0. Okay, so what was G of V? G of V was what? Just trying to, I think they might have missed a sign even here. Yeah, that's fine. Doesn't really matter because it's going to be 0. Right, so this should be a minus here, but that's fine. So that's G. Right? obviously p of xy is not a function of nu, so that goes away. This thing is a function of nu, but this thing is 0. So how do we do this? Let's see. So this is the integral of q grad nu q, right? Grad log q, right? So what was grad log q? Let's go back. Grad log q is grad q over q. These cancel. This is 1. Did that make sense for those of you who are watching? Okay. So basically, this part here goes away. This is equal to 0. So now we can just expand out g into its original form, and now we have this lovely gradient expression, right? Where everything is doable. Right? So this, we said we can sample from Q. This is called the score function right here. So sometimes it's called score function estimator, right? That's a score function. It's also called a likelihood ratio or a reinforced gradient, right? We know that we can evaluate the joint density, the log joint density, and we sure as heck can evaluate the log density of a proposal if we can compute the score function, right? So we're good. So this specifically gives us an evaluable estimator for the gradient of the ELBO. So what do we need to do in order to optimize this? And why is this compatible with stochastic gradient descent? Well, now we can do Markov Monte Carlo approximations to this integral and get unbiased gradients of the ELBO. So we can sample a few times from Q, and whatever that mini batch size is, we know that the gradient that arises from averaging this quantity, that will be the gradient of the ELBO. And if we follow the gradient of the ELBO, we'll be maximizing the ELBO, or go in the whatever. You use the gradient to optimize the ELBO. By maximizing the ELBO, you drive the KL to 0, which means that this learned Q will be the posterior distribution under this model. Pretty cool. Okay. So that's basically what I just said, right? So now we can get noisy, we should say with this particular gradient estimate, very noisy, but noisy unbiased gradients with Monte Carlo. So you sample Z from Q, you evaluate this gradient, and we're done. Okay. Now remember, this Q can be a mean field or whatever style approximating distribution you want. And in the land of automatic differentiation, this is not bad because we just have the score functions for all of the distributions in our variational family, and we can specify whatever we want here, really. So the optimization people at least see we can do a stochastic gradient here because it's unbiased, and we have unbiased gradients. We have an expectation, we've got unbiased gradients, and we can go. Yeah, we're good with that. Okay. Fine.
I have a question. It's maybe just a silly question.
Yeah.
Sorry. The function also satisfies like the L smoothness and the other typical.
So the proofs, as I'm sure you know, as optimization people, the proofs for convergence of stochastic gradient descent and so on and so forth rely upon convexity and smoothness arguments that are basically never true.
Right.
Right. But we use the algorithms anyway because they have decent properties, right?
They tend to work.
And they tend to work, right? And this is going to be the exact case, like literally no way, right? Like, there's there's a really, really interesting paper, one of my favorite papers of the last however many years, which relates variational inference and the sample path of steps taken by stochastic gradient descent to an implied variational family. It's a paper by Dave Bly and some authors, which basically say if you just do stochastic gradient descent with a constant step size, which is a little bit weird, but with a constant step size, that algorithm produces samples from a variational family, basically parameterized by stochastic gradient descent, with the variance of the variational approximation being controlled by the step size, basically.
Interesting.
Very interesting.
Do you think that could potentially explain, like, from a perspective, why it tends to work? Why these algorithms?
So this doesn't say anything about, well, okay. My strength is not this theory, but if one were to be interested in trying to explain why stochastic gradient descent works, using the tools of sort of, Markov processes in ergodic, like blah blah blah, these sorts of things, I would look in that direction. There's yes.
Okay, cool.
But anyway, so when they gave this tutorial, I was a little bit irritated because really what they should have written here is any probabilistic program. And they knew better because they actually did this BBVI work while they were working under the same DARPA grant as me to work on probabilistic programming. And this is where it came from. So the idea is, this is them selling it at NeurIPS to a certain extent, right? You can build these variational families, Q of Z given nu, out of variational family building blocks. They're just distributions, right? You can plug in massive data. That's pretty cool, right? It's not obvious from what we just talked about, but obviously we won't go into that. But I would scratch this from our discussion here and say you can plug in a Q and any model specified as a probabilistic program, run it through this black box variational inference procedure, and produce a posterior distribution. Okay.
Can I ask a question?
Please.
The black box part of this, like, I can see how you can do this as a black box, but like you're gonna need the support of your variational distribution at some point or something like that, right? Like you need to know something about this black box to make it work, to get your variational distribution right.
Indeed. So it's not quite so black box. I would call it gray box or something like that, right? But it sounds really good when you say black box. You don't need to do anything. You don't need anything. You don't need to know anything. But in fact, we've already said straight away that you need to know quite a lot of stuff, right? You need to definitely know the joint distribution, and as you've discovered, you definitely need to be able to know the support of the various distributions. But yeah, we'll get to it. So the interface though is pretty simple, and this is what is this homework for? Yeah, homework 4. Okay. So this is the second time through it, so now it should be super, super clear. So should we have a model log p x z? Okay, so for us, that's just a prog because we're more awesome and we know how to deal with control flow. Okay. And some variational approximation. So this part is not so black box, actually, not so black box. In our case, we can make it pretty black box. So actually, to make it black box variational inference, you have to use probabilistic programming techniques, actually. And the reason, at which you'll discover when doing the homework, is that the support of these random variables is something that you need to be able to extract from the program. And the support is not, it's better to over approximate the support and use some variational family that's different, that's broader than the original random variable. Okay? But we're going to talk about mean field, which is to say that for every address or for every random variable, named random variable in the program, you're going to have a variational approximation, a variational distribution, one of these Qs, and a parameter for that distribution, mu for each one of those distributions. So, but once you have that, once you specify that, which is you can programmatically specify, which is nice, then the procedure is pretty straightforward. While not converged, draw some samples from your variational distribution, pick a decreasing step size according to a Robinson-Monroe sequence, right? And then update your variational parameters with a Monte Carlo approximation to the expected gradient, where you're evaluating a weight, which is the joint, log joint minus the log proposal, and the gradient or score function of the variational distribution, which is to say the gradient of the log probability of the sample under the variational distribution with parameter nu. Okay? And this is the most black boxy thing you can have. Once you have a set of variational distributions that you compose together, then you can also abstract those to basically externalize an interface that says, okay, I want to be able to take a gradient with respect to the parameters of this distribution. And if I have a library that gives that to me, that's cool. Or if I have an automatic differentiation system that gives it to me, even better. Right? So you can do this with a library, which we talked about. Right? You can just have implementations of these for each distribution type in our variational family. Again, black box variational inference came out before automatic differentiation was in most of the modern languages, right? Or you can just use automatic differentiation to get that for various densities in the variational inference black box set of approximating distributions.
What does the Robinson-Monroe sequence actually do here?
Oh, I actually had it in the slides before. Somebody from optimization should just be able to say that right off the top of your head. So like the sum has to be the sum has to diverge, but the variance, what is it that, so somebody from we've got 3 optimization people in here. Tell me what the Robinson-Monroe criteria are. I have to look it up again just to remember it. It's also in 340, so whoever took 340, Jason, you should remember it.
I definitely don't remember.
1 over epsilon squared ends up being less than infinity, something like that.
Yeah, I'm not going to write it down until we know for sure. It's even in the book. I don't remember. Yes. So if we have rho t, then the sum of rho t is infinite, and the sum of rho t squared is less than infinity. So basically this says you can get everywhere, but steps get smaller. So you'll stop going, right? And there are sequences, there's lots of ways to construct these sequences. And you just have to remember you can, like, what are some that satisfy this. Yeah, yes, 1 over t. Sure, yeah, that will do it. Yeah. Thank you, Greg. Okay, cool. Let's take a little break here because we've got to black box variational inference, and we'll go through the rest of the stuff more quickly from today. Okay, so see you in like, I don't know, 4:37. There we go. And we're back. Okay, so we've just finished up with BBVI. But again, it's not so black box. So we have a noisy gradient. We're going to use stochastic gradient on, but we need to be able to sample from Q. We need to be able to evaluate the score, be able to evaluate the joint density, the log joint density, and the log of Q. Now, again, this is not really true. You need to be able to reason about the support of the Zs. So this is definitely not true, but when you're giving a tutorial in front of several thousand people, nobody asks questions. Sorry, Dave, if you ever watch this. Liar. Okay, so what we did in class was literally, so now we're just going to go Z goes to X, X goes to Y, nu goes to lambda. Okay, and that's basically what we did in class the other day, right? So when you look at the Prob book and you map between, right, the goal is to learn to factorize the approximation to the ELBO, minimize or maximize the ELBO. The derivation that we did before is exactly the same. It was just too fast, right? Doing this makes Q close to P in the KL sense, right? And what we will do in the Prog case is just consider a mean field approximating family, where for every variable in the support of our in our Prog, we have a variational family. We specify a variational family. Here's the Robbins-Monroe sequence criteria. Again, thank you, Greg, for saying 1 over t basically here instead of 1 over n, but 1 over t. And you follow the sequence, and you're going to get some convergence. Again, in reality, you don't really care because you don't know, and you're going to use some optimizer with some step. You're going to use Atom, for which even the formal proofs are wrong. So the estimator is a reinforced style estimator. These are the same slides we did before, where we said this thing goes to 0. We did that much more slowly this time, right? Although the derivation was there before, and we said we use R instead of G, but they're the exact same thing. Okay. And then we talked about arriving at the BVI objective, and clearly, so long as the expectation of B is if B is a constant with respect to X, then we can introduce control variates, which I think we talk about in just a second. If we don't, we can come back to this. In your homework, you're not required to implement the control variates. So the point is that when you do the BVVI evaluator implementation, instead of proposing the prior, we choose a variational proposal kernel for each random variable from which we can sample. The requirement is that the support of this distribution is equal to that of the prior. The problem is that the prior can shift. In other words, the parameters of the distribution can shift depending on the control flow or state of the program. And that causes some issue. So the support of this distribution is equal to that of really the prior under transformation. You'll consider this in program 5 of the homework. And you have to have a gradient with respect to the parameters implementation for each variational proposal kernel, and blah, blah, blah. And there's a project question here, which is this correct in the Hoppel setting? And we talked about this very briefly at the end of last lecture, where it's clear that you could implement BVVI in the Hoppel setting, but it's not at all clear whether or not it's correct. And this is still an open question, as far as I know. I haven't seen anybody prove that it's correct. There's a problem, which is that this basic BBVI doesn't work particularly well. I should say particularly well. And it has to do with the variance of the gradient. So here, what we have is a plot of the normal normal 0, 1 PDF. So this is just normal 0, 1 log normal. I guess I should write this as like log normal x 0, 1. Right. And this is the score. So this is the gradient of the log evaluated. The gradient of the log density evaluated for normal distribution. And the point is that as you get further and further away from the mean of the normal distribution, the score function doesn't behave particularly nicely. It gets very, very large. So the score for uncommon samples, if you get an uncommon sample ever, that score function can be very, very large. Okay. So this gradient can be high variance, right? So
Can you remind me what happens when the score is large? I kind of forgot what the score really means.
Score function is literally this. It's the gradient of the log density. So
why
go ahead.
Why is it bad if it's large?
It's really it's more about so it's more about so what's the okay, fine. So what's the variance of the gradient? Well, the variance is equal to the expectation under Q of the gradient squared, right? And basically, this is just shorthand for the gradient of the elbow here, and this is the gradient of the elbow here, right? And if this value gets large, the score function gets large, then squaring it's going to get large, even larger, and that's the variance of the gradient. So we have an unbiased gradient, right? But if it's unbiased, but the variance is all over the place, then your stochastic optimizer is going to suck because you're going to really, really walk like a drunk person, right?
I see.
Right.
Mm-hmm.
So what we want to do is we want to control this variance in some sort of a way, and this is basically where this idea of control variates comes in. It's where you replace f, which here is the function that we're optimizing in the expectation. So there's an expected value here, right? So we're going to replace f in such a way that with an f hat in such that in expectation, our f hat is equal to our original objective. Okay, and a general class that looks like this is this, right? So if you take if you just look at the expectation here of f hat, right, what's going to happen? Well, that's equal to e of f minus e of this thing, right? Which is going to be minus a e of hz minus e of hz. Oh, look, okay, so that's a 0, right? So this thing, so that's a 0. So this thing, a class of control, we'll call it a control variate class, is one in which you take the original f, whatever this thing is that we're optimizing, which again is going to be, you know, our or whatever is inside the expectation, which is just going to be this thing, right? Our gradient expression, and you replace it with an f prime such that of this form, right? Fine. So h is a function of our choice. A is choosing to minimize the variance, and a good h would have high correlation with the original function. Okay. So fine. This is cool, and we don't have to think about this. A nice thing to do, a simple thing to do, is to set h to be the gradient of the log, basically the score function. Right? Because we already know that the expectation under Q of the score function is 0. We derived that, right? In other words, yeah. So we can construct basically this is just a way of controlling the variance for the reinforce gradient computation, right? So we have our original objective minus this thing, right? We know that the expectation is 0, so all we do is we stick h in here, and h has this form, and this will reduce the variance of the gradient and make variational learning more efficient, because the gradient is the gradient is still unbiased, but the variance of the gradient is lower. And there are zillions, hundreds of papers about control variate schemes. And what's sort of funny is that Andre Mini and I talk about this a fair amount, and my lab and the control variates labs go back and forth on whether or not control variates are good or just changing the objective is better. Control variates are good and changing the objective is better. And we'll talk about this later on, where when we talk about some of the variational objectives, we can actually formulate them in ways that are lower variance by construction, basically. So when Andre and I talk about this, Andre is like, "Oh, you keep undoing my work," and then he comes up with a better control variate scheme, and it's good. Okay, and also there's some funny stuff that shows up. So like we've assumed this to be 0. It turns out, I think I even remember some work in which actually doing another expectation inside here ends up being like even lower. There's all sorts of stuff that you can do, but control variates in general are a good idea. They really can dramatically reduce the variance of your gradient. Okay. So these are the quote unquote black box criteria. Can we make additional assumptions that are not too restrictive? And this moves to pathwise gradients of the ELBO. And we're going to do this very quickly. We're going to come back to this probably and do this again because it's something that's pretty important. But this is going to be important. We're going to talk about this. We're going to talk about this a fair amount. So this is referred to as the reparameterization trick. It's also just known as change of variable. Okay. But for a second, let's say that our latent vector z. Now we're going to think vectors. We can do this more generally. And Prog again is about doing this more generally. But let's assume that z is some deterministically it can be computed, like that z can our random variable z can be generated by deterministically transforming some elementary random variable epsilon in such a way that after having sampled epsilon from S and deterministically transforming it through T, the resulting distribution on Z is as if it were originally sampled from the Q that we are interested in, the one that we wanted to specify. Okay. So a canonical example of this is the parameterization of a normal density. This is actually how you sample in reality from a normal parameterized by a mean and a standard deviation or a variance, right? You sample from a unit normal, and then you scale that value by the standard deviation, add the mean, and that gives you a deterministically transformed normal 0, 1. So we have a normal 0, 1 random variable epsilon, we deterministically transform it, and it becomes a normal mu sigma squared random variable. So this is standard procedure, right? So this is an example, but let's assume that we have a structure sitting behind Q that allows this to happen. So we're going to sample some random variable and then pass it through deterministic transformation, and that gives us our sample from Q. Okay. Now, the next thing that we want to make as an assumption is that the log joint density and log QZ are differentiable with respect to Z. We've made this assumption before. When did we make this assumption? That the log joint is differentiable with respect to Z?
It's in the chat.
Oh, thank God, at least 2 people put it in the chat. You're working on the homework right now. So this is the HMC assumption, which you know doesn't apply to all probabilistic programs because you've got branching and non-differentiability lurking all over the place. But so now this is where like modern variational inference methods in this talk diverge from probabilistic programming in the general sense, right? The reparameterization is incredibly important, and many of the people on this in this class are well aware of how important it is, right? But it's not the only thing that you can do. It's not the most general thing that you can do. So the pathwise estimator looks like this, right? So we've assumed that this change of variable can happen, right? In other words, basically, whenever we see Z that's sampled from Q, we can rewrite any expectation with respect to Q. So here's an expectation with respect to Q as an expectation over the random variable epsilon being sampled from S, and then whatever the function is, G, right, evaluated at the transformed value of this epsilon distributed, this random variable epsilon, right? Because this is equal to Z, right? And necessarily computing an expectation over S of epsilon of this G of Z is the same thing as computing over Q if you didn't have the variable transformation. So in other words, we can do Monte Carlo estimates of this as well, where epsilon K, I don't think they actually wrote that here, is drawn from S. So now we have the same problem that we had before, which is we have an expected quantity, and this G is the same G that we had before, right? So this G is the ratio, the log density ratio. But we want to maximize the ELBO. This is the same thing that we're doing, but we're going to assume that Q is reparameterizable, which means that we can rewrite the ELBO maximization as the gradient of the expectation over this the distribution of epsilon with G evaluated at the transform value. Okay, so if we just start plugging stuff in, we exchange the gradient operator with the expectation, right? And then again, we use chain rule. I guess it was product rule before, chain rule here, where we look at dg d of this quantity, d of this quantity, right? And then d of that quantity, dv, right? So we could have introduced a variable named b here, right? It doesn't really matter. So t of epsilon nu is some variable at some value, and we just use the chain rule here. Okay, but t of epsilon nu is in fact just g of z, right? Or sorry, t of epsilon nu is z, and then this is dg of z. So that's what this line here is. This is dg of z, dz, and then dt epsilon nu is whatever it is, d nu, right? So if we plug in the value of g that we have from the ELBO, then this yields, right? So this is the gradient of g times the gradient of t. Okay? And this is the reparameterization gradient, okay? But now, like we just said, we assume that both of these distributions are differentiable with respect to z. Which is not going to always be true in the case of probabilistic programs. We can make it true for Q by design.
Can I ask a question?
Yeah.
It's like I'm a little, and like maybe if I was a little bit fresher, I would just understand this immediately. But right now I'm taking, in homework 4, I'm taking derivatives of Bernoullis and categoricals, and that's all fine, right? But you run into issues with the reparameterization trick.
You're computing the score function, which is a derivative of the likelihood,
log density.
The log density, right, with respect to its parameters. And basically, every distribution is differentiable with respect to its parameters. What is not true is that Bernoulli and categorical distributions are differentiable with respect to their data.
So what I was going to say is that it's in this t, right? It's in this transformation function. That needs to be differentiable.
So the t is the same thing. Well, it's not the same thing. It's close to what you all are going to do in homework 4, but not really, because that's just a deterministic transformation. But if you think about the control flow in P of x comma z, right? Some of these z's are going to be discrete quantities, right? They're, in general, they can be draws from a categorical distribution or a discrete distribution or whatever, right? And now there is no gradient. Only when okay, so that I think I misspoke there. Let me step back. The control flow is going to be deterministic, so you should be fine. right? That's that I lied. So you'll be fine. The Z's, you're okay. Discrete distributions do not have reparameterizable forms. So you can't find a reparameterization for a discrete distribution. Done. So you're left with them still actually being in there, and you have to actually do the reinforced trick for them. That's basically what if you understand what I'm saying right now, then you're done with deep probabilistic programming. So you've got, you know, reparameterizable and non-reparameterizable variables in the same trace. Deal with it. That's deep probabilistic programming, right?
So that was actually the second question I was going to ask. Like in a sort of homework 4 setting, can you just say that, well, you know, it's just some likelihoods anyway. I'm just going to reparameterize everything that I can, and I'm going to do the score function on what I can't. Is that a fair way to go about it, or
there's just a little bit of there's just a teeny tiny little bit of subtlety, but yes, yes.
Okay.
Yeah. Any other questions? Good question. Oh, I see we're out of time, but that's okay because we're basically done. Even though I think it looks like that I have many more slides, there really are not. Because this is it. I'll flip through just to remind. Yeah, I think this is not a bad. Yeah, look, see, it's great. So we have two different estimators, and they place different demands on the model families in which you can do variational inference and the way you do variational inference. So in the score function setting, right, you need to be able to differentiate, in particular, log Q here. So you differentiate basically you have to compute the score function, right? It works for discrete and continuous models, or models with discrete and continuous variables in them, right? Because it doesn't require reparameterization. You can use all kinds of variational approximations, but the variance of the gradient can be a big problem because of the score function. So you need control variates and other kinds of schemes like this. When we talk about reinforcement learning as inference, by the way, this score function estimator or reinforce estimator is going to show up again, big time, because basically when you're computing, when you're doing marginalization in reinforcement learning, you have to integrate over discrete choices when you take actions. Okay, and if those actions are in a discrete control setting, then the control is not reparameterizable, and you're right here in this setting. So this is going to show up again in RL as inference. Pathwise requires you to differentiate this function, right, which requires your model to be differentiable, which again is maybe not the right way of saying it, but more to the point, you can't use non-reparameterizable distributions. So that's really what it's saying. You can't use non-reparammed dists, right? So in other words, the variational approximation writ large has to have this form, right? But it's generally speaking better for inference network and model learning, both. So the problem is the probabilistic programs have a mixture of both reparameterizable and non-reparameterizable distributions, and we'll talk more about that at a subsequent later point in the class. Lovely. Thank you very much for your time. If you have questions, please feel free to ask them. Hopefully that made the variational inference thing make more sense. That's the critical part. No questions? Nobody's gonna rise up? Just stressing about this homework?
Do you think about it? You said you'd think about it.
I think I think a reasonable thing to do is to just in order to keep the administrative load down, tolerate resubmissions of this homework up to the due date of the next homework. But the next homework does not change, period. We cannot push that out. Otherwise, we would just not get through the stuff we need to get through. So next homework, not changing.
Sorry, does it basically mean that you have extended until the next homework?
So there will be a small penalty for those of you who have actually submitted. Obviously, there will be some sort of discount applied to the submissions of this homework that are late, and we'll make that up as we go. It's not going to be severe, but we want to make the people who have actually submitted be rewarded for submitting on time. So that also means you're not going to get feedback on this homework, which sucks, right? So for those of you who have submitted full submissions, we'll grade them. But other than that, yeah. Okay. All right. Any other questions?
Any hints on the last program, the Dirac distribution?
Don't do it, and you know, the ultimate cost of not doing it is not so bad. The other thing is to cheat, and so like really what I want to do is put these sorts of issues out in front of you. That's really what it's about. So creativity of any kind is acceptable, really. One is you could take a limit of an approximate Bayesian computation if you wanted to. So in other words, you could fuzz the likelihood and then anneal the temperature basically of that thing down to 0 or something near 0. You can talk about ways of analyzing the program, and this is super fun. Like if you disintegrate the program, you can actually transform the program into something that you can sample from directly. But the general purpose way of doing that transformation is complex, and you have to go read Ken Shan's paper on disintegration, and then talk about how to do that in general. So one way you could do it, just for the fun of it, is you could put that program, you could transform that program into a Hakaru program, and have Hakaru then emit a new program that you can sample from. But in general, this is something to encourage you to think about potentially. For those of you who are like more theory motivated in particular, think about potential projects related to hardness of computation. Do I expect you to get in? Do I expect any of you to? In the last incarnation of the class, only one person produced an interesting result for that, and they did horrible hackery, basically, to for instance, constrain their MH steps to be joint steps in the constraint space, which was not general in any kind of a way, but at least produced results. So the other way of thinking about it is the only way you can possibly get an acceptance in that is if you do correlated steps. Right? You can't. You have to do block block updates. And if you update such that the constraint is satisfied, you're going to mix, right? But you have to exactly satisfy the constraint, and some thoughts and writing about how one might satisfy such constraints in general is something interesting, legitimately interesting to think about, right? And mathematically, it's interesting because you're conditioning on a measure zero set. Right? Or a measure zero event. But there's clearly an answer. So like there is, in other words, there clearly is a posterior distribution, but how to arrive at it involves disintegration. And that's in general hard. We haven't covered it, but I'm hoping, it's a grad class. You all are independent researchers, so you can look up some of these things. More? Can everybody go off and implement BBVI now? Like I would hope at the end of this lecture now you could really go off and implement it. It shouldn't be straight. It should be once Bernd is the is the support code uploaded?
It is, but I see that in my haste I accidentally uploaded it to my personal GitHub, so it's not available anywhere yet.
Okay, so it should come up this evening or something like that. Yeah. So
it's there. It's there. It has an example in it to show you what you can do with it, to give you sort of a 2-word overview of it. It just gives you some distributions that are redefinitions of what PyTorch defines for you. And it's made in such a way that, first of all, you can really easily get access to parameters and optimize over them. And secondly, it implements some basically parameter constraints by transforming the parameters to something that doesn't have any constraints. Is that a fair way of describing it?
For the optimization people, it changes the optimization problem from a constrained optimization problem to an unconstrained optimization problem, which everybody will like.
Right. So with all that support code, how hard is this going to be for those of us who are not doing Python?
You need some kind of distribution object that has a sample function. It has a log prob function, and that log prob need to be differentiable with respect to the parameters. That's in principle, that's all you need. And then you need to have some sort of, like if you want to make this into an unconstrained optimization problem, like, you can take a logarithm of some parameters, something like that,
Okay.
Should be too hard.
Basically, all of the functionality that Bernd has put together is stuff that can be composed from deep learning libraries very straightforwardly. So you can basically take what's there and look at it and say, I see. Okay, so I need a softmax here, and so on and so forth. It's really not that bad. But from what I understand, you Julia people, I don't know, are you also operating in Julia?
Not for this one, but I do a lot of Julia stuff.
Okay. But yeah, whatever language you're operating in, if it has a deep learning framework, you should be able to construct most of the stuff. But the Julia people apparently are having problems with gradients now anyway, so I don't know what's up with that. I have to talk to Adam and Ryan to know for sure. All right. Well, I'm not hearing a huge number of questions. Just everybody's, busy. So good luck. Thank you very much for your time, and I look forward to seeing you on Thursday. Cheers.